All right, let's take a look at the titration of weak acids with strong bases. This is a little bit more complicated than the one that we perform with strong acids and strong bases. And the reason why is because unlike the strong acids, which fully dissociate in solutions, if you have 1 molar concentration of HCl, you're guaranteed to have 1 molar concentration of H+. In the case of weak acids, if the concentration is 1 molar for the weak acid, the concentration of H plus is going to be less than that. How much less is going to determine on the initial concentration and the extent of the equilibrium constant of the weak acid. So when it comes down to finding the initial pH of the solution, which is the pH when you haven't added any sodium hydroxide, you basically are dealing with your typical ice-stable problem. Okay, so I'm going to make it very specific. Let's say that the weak acid we're dealing with is nitrous acid. Dissolving nitrous acid in water to make a solution, an acidic solution, will ultimately result in a reaction where you form the conjugate acid nitrite and the conjugate base nitrite and the conjugate acid hydronium. Alright, so what we're going to do is set up a typical ice table. And in this problem, there we go. In this problem, the initial concentration I'm going to refer to is 10 to the negative second molar for HNO2. The K value of HNO2 is 4 times 10 to the negative 4. So we're going to try to find the pH based on that info. The initial concentration of HNO2 is 1 times 10 to the negative 2. The initial concentration of hydronium and nitrite, those two are 0 because we haven't been told anything in regards to their concentrations. The change in concentration for this reaction, which is 1 to 1, is minus x, and plus x, meaning that the equilibrium concentrations are 10 to the negative 2 minus x, and plus x. Alright, now we use that information to figure out the value of the hydronium concentration. So we need to input the concentrations at equilibrium for each one of the species, which means that we'll end up with x squared on the top, and we'll end up with 1 times 10 to the negative 2 minus x on the bottom. And that equals the Ka value for HNO2. Here, if you do divide 10 to the negative 2 by 10 to the negative 4, unfortunately, you will not get a value greater than 400, so we have to keep the minus x. So we're going to cross multiply both sides by 10 to the negative 2 minus x to yield the following equation. We add 4.0 times 10 to the negative 4x to both sides, and we subtract 4.0 times 10 to the negative 6 from both sides to yield the following quadratic setup for the quadratic formula. Okay, so the value of B is positive 4.0 times 10 to the negative 4. The value of C is negative 4.0 times 10 to the negative 6. So we're going to input all of that into the quadratic formula. 4.0 times 10 to the negative 4 squared minus 4 times A times C, all divided by 2 times A. So if you follow the rule of thumb, right, you're going to ultimately negative and negative become positive. So you're going to multiply the values here, 4 times A times C, and ultimately add them to B squared to get the following value. Take the square root of that number and add it to negative 4.0 times 10 to the negative 4. Press enter and then divide by 2 to get a value of 1.81 times 10 to the negative 3. That's the value of x. Now looking back at the table, the value of x is literally the value of the hydronium concentration. So what we need to do now is take the negative log of the hydronium concentration, which will now give us the pH. So the initial pH before you start the titration for the acid solution is 2.74. So we're going to input that, and yes, by the way, this is less than pH of 7, confirming that this is in fact an acidic solution. So we're going to input that for the initial amount. The initial amount of the acid has an original pH of 2.74. Alright, now we're going to see what happens when we start adding sodium hydroxide. In other words, when we start the titration itself. Alright, and because adding strong conjugate base will convert some of the conjugate acid into conjugate base, we will now generate a buffer in the first steps of the titration. So this is the way it's going to go. You need to know the following in order to perform the calculations that we're about to do. Not only must you know that the concentration, the initial concentration of HNO2 is 10 to the negative 2 molar, you need to know the specific volume that you have present. So right here I'm going based on the premise that we have 50 mLs of the 10 to the negative 2 molar HNO2 solution. And the first thing I'm going to do is see what happens when I add 1 ml specifically total of 0.100 molar sodium hydroxide to it. Alright, and the idea is this. The moment you add sodium hydroxide, water is no longer the best base present in solution. The best base, the moment you add hydroxide, is hydroxide itself. So HNO2 will no longer want to react with water, it will want to react with the best base, which is hydroxide. And so you have to change your equation ever so slightly. HNO2 reacting with hydroxide will still generate NO2 minus, but the hydroxide will now generate water, no hydronium. Alright, now this changes things a little bit because not only are we changing the equation from the acid dissociation equation, but the thing is that unlike water, hydroxide is in fact a strong base. And what that guarantees is that the reaction, the neutralization reaction going on here, is guaranteed to go to completion. Meaning that we're going to have to find out which one of the two reactants is the limiting reactant. And based on that, we need to determine how much of the acid is going to react away, how much of the conjugate base we're going to end up generating, and ultimately we're going to use that to determine the pH. So this is a process that involves knowing the initial concentration of the acid and its initial volume, along with the concentration of the base with the volume of base that's being added. And I'm going to introduce a new concept. So I showed you in the previous video that if you multiply the volume by the concentration, you get the moles. That's if the volume is in liters. But if you were to keep the volume in milliliters and you multiply the volume in mLs by the molarity, you automatically get the millimoles of the substance. It's a nifty little trick that you can use to kind of get to the point, just like bypass an extra step and make things a little bit simpler. Also, you end up dealing with numbers that are not super small, so you don't need to write exponential numbers necessarily. So what I'm doing right here is multiplying 10 to the negative 2 molar by 50 mLs, and I end up with 0.5 millimoles. And over here I multiply 0.1 molar by 1 ml, and I end up with 0.1 millimoles. Alright, so if you were to change the volume to liters, then this will just be regular moles, but you will also end up with an exponent that will be 1,000 times smaller in magnitude. Alright, so what we're going to do is we're going to generate and fill up a table. This is not a nice table, however. It's semi-related to it, but it's a little bit different. This is a table that one of my previous TAs dubbed a mice table. Mice for molarity, initial molarity concentration of the species, followed by the initial millimoles of the species, followed by the change in millimoles, and the quote-unquote equilibrium amount of millimoles at the end of the reaction. Alright, so this is the way it goes. You have the initial concentrations, right? And technically we've already accounted for that. We have 10 to the negative second up here and the 0.1 molar concentration for hydroxide. There is no concentration for NO2 minus to begin with. The initial amount is simply obtained by multiplying the volume by the molarity. So that's the 0.5 millimoles and the 0.1 millimoles of hydroxide. As of now, we have no millimoles of nitrite. The change, and now this is the big change from the ice table problems, the change is not based on X, because unlike the typical ice table problems where we don't know the extent of the reaction, here we are guaranteed to drive the reaction to completion. So all we have to do is recognize which one of the two reactants is the limiting reactant. And the simplest way to do this is to look at the numbers, right? If this is a 1-to-1 reaction, whichever of these two numbers is the smallest one is automatically the limiting reactant. And between HNO2 and hydroxide, hydroxide is the least amount. So that becomes a limiting amount in the reaction, meaning that for the change, you're not going to be subtracting minus X from hydroxide and HNO2. You're actually going to be subtracting the negative 0.1 millimole because the reaction is going to completion. And for the product, you're not adding plus X to it, you're adding 0.1 millimoles. Alright, finally, all you have to do is carry out the subtraction. 0.5 minus 0.1, 0.1 minus 0.1, 0 plus 0.1 to give you 0.4 millimoles for the conjugate acid, 0.1 millimoles for the conjugate base. Alright, so this is the mice table that allows you to get to those values. And by the way, much like your ice tables, I actually found out that there are actually some channels on YouTube that show you videos of little mice eating on the tiny little dining table. So there's actually mice tables, although technically some of these things here, some of these animals here are gerbils, but you know, you get the idea, mice tables. Alright, so what we're going to do is use the information we just gathered from the mice table to figure out the pH of this solution. And the idea is that you have amount of conjugate acid present and amount of conjugate base present, and they're both weak. So we can actually go ahead and use the Henderson-Hasselbalch equation. And the beauty of this is that because in the Henderson-Hasselbalch equation, and notice that I'm getting the pKa right now, pKa of this substance is 3.40. Because in the Henderson-Hasselbalch equation you're dividing concentration by concentration, you do not need to change the millimoles back to molarity. That's something that you need to do for an ice table. The ice table has to be molarity. But with the Henderson-Hasselbalch equation, if you were to change this to molarity, you're going to be dividing the millimoles of HNO2 by some amount of volume. In this case, the volume will be 51, right? That's the total volume. But you will also be dividing NO2 minus by 51. So by the time you carry on the ratio, the 51 mLs that you divided each of these things by will cancel out anyway. So instead of wasting time doing that extra step, simply go ahead and input the number of millimoles of the base on top and the number of millimoles of the acid on the bottom. It's the same thing as inputting the concentrations. So carry out that division, take the log of it, you're going to find out that that equals negative 0.6. So add the negative 0.6 to 3.40, which is the pKa, and you'll find out that the pH after adding 1 ml of hydroxide is 2.80. One common mistake that happens at this point in the calculation is that people will look at the pH and they'll say, what the heck, I added hydroxide, why is the pH acidic? If you're adding hydroxide, the pH should be going up, but this looks like acidic. And on top of that, they'll make the mistake of saying we subtracted a value from the pKa, so instead of raising the pH, we lowered it. But this is what you have to remember. This is the pH based on the initial amount that you started with. And if you go back to the table that has the drawing, the actual graph of the titration curve, you'll realize that the initial pH was 2.74. And upon adding the 1 ml of hydroxide, you indeed increase the pH to 2.80. Not by a lot, granted, but you did increase it by some amount. So the idea that you are adding base and the pH has to go up is actually working out. Just remember that you have to reference it back to the initial pH value that you calculated at the very beginning. Alright, we're going to do 2 more calculations in the buffer region before we finish this video. So let's see what happens when we go up to a total volume of 2 mLs of hydroxide. Now we have 2 mLs of hydroxide, multiply the molarity by the volume, you still have 0.5 millimoles of the acid to begin with. But now you have added 0.2 millimoles of base. So when you get to your mice table, you have 0.5 millimoles of HNO2, 0.2 millimoles of hydroxide. Hydroxide is still the least amount, so you're going to subtract that from both reactants and you're going to add that amount to the product. Meaning that you will end up with 0.3 millimoles of HNO2 and 0.2 millimoles of nitrite. At this point, switch over to the Henderson-Hasselbalch equation. The pK is still the same since it's the same acid that we're dealing with. So we input 3.40 plus the log of 0.2, which is the base, divided by the acid, which is 0.3. You're going to find out that the log of that ratio is negative 0.18. Added to 3.40 tells you that the pH is 3.22. And looking at the graph, you see that the pH has gone up yet again upon adding that extra ml of hydroxide. So let's do this one more time. Actually, we might do 2 more times. We're going to go and see what happens when we add 2.50 mLs of hydroxide. So in this case, you still have 0.5 millimoles for the acid, but the hydroxide now it's equal to 0.25 millimoles. That's still the least amount of millimoles for both reactants, so you're going to subtract 0.25 from both, and you're going to add 0.25 to the product. So what ends up happening is that you end up with 0.25 millimoles of HNO2, but you also end up with 0.25 millimoles of nitrite. And so basically what you have accomplished by adding that exact amount of volume of hydroxide is that the conjugate base and the conjugate acid are going to cancel out, and you have basically reached the region where the pH equals literally the pKa. This is known as the midpoint, the point where you have added exactly half the amount of hydroxide as you had acid to begin with. Alright, so, and if you look at the graph right here, we have still raised the pH by adding that extra half ml of hydroxide. So we're going to do this one more time. We're going to go up to a total amount of 40 ml of hydroxide added. So now we have 0.5 millimoles of acid that we begin with. We have added now a total of 0.4 millimoles. So based on the ice table, the limiting reactant is still hydroxide. So you subtract 0.4 from both and you add 0.4 to the product. So now you have only 0.1 millimole of acid remaining and you have 0.4 millimoles of base produced. So in your Henderson-Hasselbalch equation, you will input 0.4 millimoles for the base, 0.1 millimoles for the acid, carry out that division, take the log of it, you're going to find out that that equals positive 0.6. So add that value to 3.40, the pKa, and you're going to find out that the pH have now been raised to a total value of 4.00. All right, that concludes the buffer region and initial pH readings of the titration curve. In the next video, I'm going to show you how to calculate the equivalence point. And this is the part of the titration that is the hardest because it's going to involve keeping track of multiple reactions and multiple events happening in the course of adding the exact amount of hydroxide base as we did have acid. So I'll see you in the next video.